be solids dissolved in a liquid. And then also the weird one, maybe it's just weird to me, but solids dissolved in other solids. It's like most of the metals, like steel is a mixture of solids. Huh?
They don't melt them together?
Oh, I mean, they have to melt them to mix them, yeah. But then when it solidifies, it's still a mixture. Yeah. So dissolving, what's up with that? Right? If I take salt and I put it into water, what happens to it? Dissolves. It disappears. And then this is the one that usually gets people, right? Because it's still in there. So if I take that water and I boil all of the water away, the salt is left behind. And I was thinking like this, we should just do this as a lab at some point because just see it. Just boil water. Yeah. I mean, you can literally take tap water and if you boil it away, there will be stuff left behind. And that's actually the stuff that makes hard water deposits. So like when you get water that splashes onto things and then dries and then splashes and then dries and splashes and then dries, it leaves the salts behind. And once they form those crystals, they're hard to get rid of. Right? So it dissolves, it disappears. It means that it's just spread out into the solution. And what's actually happening is that the water is engaged in a tug of war with the salts or the ions that make up the salt. So the water molecule, we talked about polarity, has a positive side, which is the side that's going to have the hydrogens. It's going to have a negative side, which is the side with the oxygen. That negative side will pull on the sodium. But that sodium is also next to a chlorine. The chlorine will pull on that. And this tug of war happens. Now, for salt, we all know that it dissolves pretty easily. So water wins this by a landslide. And essentially, as soon as you put that sodium chloride crystal into the water starts ripping it apart. And it takes all of those sodium and chlorine atoms and just spreads them out and rips them up, and it surrounds them, and the water will actually form little bubbles of water around each of those ions. Now, that doesn't happen with everything. Much earlier in the semester, we talked about things that were insoluble. We did precipitation reactions. It's a long time ago. So for salt, table salt, the water wins that tug of war. But for other things that aren't soluble, especially those hard water deposits, the hard water deposit holds on to its ions better than the water can pull them apart. And so they don't actually get removed very much. We do have to talk briefly about electrolytes. They're what plants crave. Have you guys seen Idiocracy? It's a great movie. Yeah, Brondo. Yeah. So this is like a future where like everybody has a very, very low IQ. And basically they take their Gatorade and they put it on everything. And they're like, it's Brondo. It's got electrolytes. It's what plants crave. But now all their crops are dying, but nobody realizes it. It's got too much electrolytes for plants. The thing that you're talking about in electrolytes is usually different types of salts because we need those, and when you sweat, you lose those. So the electrolyte solutions have these different ions in them. Sodium would be one, magnesium, potassium. It's usually the positive charged ones we care about. But you can also have what are called non-electrolyte solutions. And this is where you have a molecule that gets pulled apart. So the key thing here is that the electrolytes have charged particles, non-electrolytes have neutral particles when they get ripped apart. And we skipped this lab, which is unfortunate, but if you we've got these like light bulb apparatus where you plug them into the wall and you stick them into the solution and the light bulb lights up, or it doesn't. If you do this with sugar, which are dissolved molecules, it doesn't light up. If you do it with salt water, it lights up. If you do it with weak electrolytes, it kind of lights up. All right. So I said some things dissolve, other things don't. Earlier in the class, we talked about this in terms of just like a yes, no, does it dissolve? Sodium chloride, yes. Magnesium carbonate, no. Now we're going to talk about it in terms of the amount that can be dissolved. And for this, it's always in terms of 100 grams of water. So solubility says the maximum amount of solid in grams that can dissolve in 100 grams of water. So our grams of solid, that would be our solute. oh, I want to get these colors right because I color coordinated things later. In 100 grams of water, which is our solvent. Right, so grams of solid, that's the solute. This is the solvent, which may be kind of weird outside of chemistry if you've never thought of water as a solvent. You might think of things like acetone or paint thinner, toluene. But to calculate this, we basically calculate the number of grams of solid divided by 100 grams, or actually not even divide by, but per 100 grams of water. So it could tell us how much table salt we could dissolve in 100 grams of water. And this is telling us the maximum amount. So the solubility, the maximum amount that I can dissolve of sodium chloride is 36 grams per 100 grams of water at 25 degrees Celsius. So in other words, if I take 100 grams of water, I put that in a cup, I weigh out 36 grams of salt, I can dump that in there, and all of it should dissolve. Assuming it's 25 degrees Celsius, which is like a little bit warmer than room temperature, and that does matter. And that would give me, if I put that 36 grams into the 100 grams of water, that would give me a saturated solution. Meaning I can't put any more in. It's kind of the same idea, like if you take a sponge and you like soak it in water and you take that sponge out of the water, like it is saturated with water. It is completely full, can't take any more water. In fact, if you take it out of the water, it'll drip out. We're doing the same thing, but with the solid dissolving in the liquid. So if I take more, I guess if I take that sponge and I try to add more water to the sponge, what happens to that extra water? It just drips off, rolls out, like it doesn't go into the sponge. Same thing here. If I've dissolved 36 grams of sodium chloride in my 100 grams of water and I add another gram of sodium chloride, it won't dissolve. It'll just go to the bottom and it'll sit on the bottom. Even if I added half a gram, it won't dissolve. I'll have some sitting on the bottom. And that's actually one of the ways that you can tell that you have a saturated solution. So I have a solution, I try to dump some salt in there. If that salt stops dissolving, then I've hit that maximum threshold.
If you put like 40 grams with 100 grams of water at 25 degrees, will it all dissolve? Or will it partial?
Good question. So yeah, the question was, if you take 40 grams of salt and put it in 100 grams of water, what would happen is 36 grams would dissolve, and then 4 grams would be sitting on the bottom. Give or take, depending on how close you are to 25 degrees Celsius, how pure your water is, you know, details. But yeah, for the most part, 4 grams would just be sitting there on the bottom.
Does high temperature mean more dissolubility, or is it lower temperature?
Great question. Temperature affects solubility. So I found this chart, and I think this is real data. You can see that it's like a little bit lumpy. Increasing temperature generally increases solubility. That's what you should remember for this class. If I increase the temperature, more stuff should dissolve. The amount that happens depends. So what am I looking for? Oh, I wanted to highlight that. Higher temp equals more soluble in general. So you can see here, but this is 2040, so like 25 is here, and that's 36. So as you increase the temperature, if we wanted to dissolve that 40 grams, we'd have to go all the way up to 100. Yeah, basically boiling water, and that doesn't even look like it quite makes it.
Have to do with like the way that the particles move and like that's the explanation of that.
Yeah, so right, increasing the temperature increases the motion of the particles. And so in that tug of war between the water and the salt, if the salt molecules are already moving more, and if the water has more kinetic energy, then this bond is easier to break. The water also does a better job at pulling the salt away from the rest of the crystal. So there's more energy available to sort of spread out and pull apart that solid. So for most things, there are some things where increasing temperature decreases solubility. I could not tell you why. I didn't look into it that much. Okay, so solubility of sodium chloride at 80 degrees C. If we look on our chart here, 80 degrees C is about, yeah, 38.4. Sounds good. So you'd say that's 38.4 grams of NaCl per 100 grams of water. And you might want to say at 80 degrees C, although that isn't the question. And like, yeah, this kind of thing, like put a question like this on the test, and it's like, read the chart, do your best, try to get in that ballpark. Like I wouldn't want to see anything less than 38 or anything more than 39, but like 38.5, you're eyeballing it, so it's going to be off a little. Okay, so now we've got this 38.4 grams at 80 degrees C. And now what if I let it cool down? Cools all the way down to 25, which is where I can only have 36.
So does the deposit just fall on the bottom of it?
Usually, yeah. So usually as you're cooling it down, we're losing energy from the water, and those sodium and the chloride molecules can find each other again, and they start to stick together, and they start to form solid, and you'll start to see crystals form out of the solution. And we can actually do the math to say, if I have 38.4 grams of NaCl dissolved in there, 80 degrees C, I would subtract out and say, okay, at 25-ish, that's 36. Then that should give me something like 2.4 grams of NaCl that will recrystallize. Yeah, did that right. This is a little bit weird because it's like you would think, oh, that's 20, so 25 should be halfway, but it goes 20 to 40, so 30 is in the middle. So it'd be like a quarter-ish, yeah. Yeah, so if you cool things down most of the time, for almost everything, you cool it down. If you have extra solid that's in the solution, it will start to form crystals. It'll start to precipitate out of the solution. And this is actually a method. These are actually salt crystals. Like the really, really fancy chefs want these funnel-shaped salt crystals. I found a whole procedure for actually growing. So the actual crystal shape of salt is like a perfect cube, and it'll be clear. And I found a whole procedure because I was just looking for pictures of salt crystals. But I found this like really nice detailed procedure for like growing those salt crystals. I can share that on Discord if somebody reminds me. I saved it. Probably gonna do it at Friday Night Lab. But this is a way that you can increase the purity of something. If you're doing some sort of chemical reaction, you produce a compound, but it's mixed in with all this other stuff. If cooling things down will cause it to precipitate and be less soluble, you can start to form crystals. And in some cases, what you do is you take your impure stuff, dissolve it in just enough solvent at a high temperature, then cool it back down. When those crystals form, they want to form crystals with other things that are the same compound. So if you do this with sugar, then the sugar molecules will form crystals selectively. The sodium chloride will form crystals selectively. And you can increase the purity once you take that solid away from the rest of the solution. Now, I said most of the time, because in rare cases, you can end up with a supersaturated solution. So a supersaturated solution holds more than the normal soluble amount. Why? Usually it's because the crystal or the individual molecules that wouldn't normally be soluble have a hard time finding each other. And you need something that's called a nucleation site. So that becomes the nucleus or the beginning point for the crystals. Sodium acetate, which is the salt vinegar, is really easy to make supersaturated. And then if you take, so like if I made a salt solution that was supersaturated, cooled it down really, really carefully, and then added 1 grain of salt, all of the salt that couldn't form before will form instantly at that point. Or if you pour it, sometimes just shocking it is enough and crystals will start to form. They form really messily, like you won't get nice ones like this. These have to form very slowly because the faster the crystal forms, the more it traps other things and the more it forms in a disordered manner. So that's recrystallization. So I said some things will decrease. We don't have any examples of that. But this is sort of a messier plot, but it shows us that like the amount that temperature affects the solubility of something really depends on what that thing is. So sodium chloride actually has a very, very flat curve. So it's not very dependent on temperature. But something like potassium chlorate or potassium chromate, I think it's potassium dichromate, potassium chloride, like these all have much, much steeper curves, meaning that if I change the temperature, I get a huge difference in how much can dissolve. So if we look at this and we say, okay, I've got 40 grams of potassium chloride in 100 grams of water at 80 degrees C. And we're asking the question, is this undersaturated, meaning am I below that solubility? Or is it supersaturated? Is this above that solubility? So like 80, and we're gonna go up to the KCl, which is 40. But the actual KCl line is up here. So I've got 40 grams at 80, roughly. That line didn't go exactly where I wanted. But I could have 50, maybe like 51. So we're below the solubility line. So this represents like our ceiling for solubility. So because I'm below that, this would be undersaturated. But what if I change the temperature? So I still have 40 grams of KCl, but now I've cooled it down to 10 degrees Celsius. Yeah. So kind of can just take our line here because we started with 40. And if I cool this down to wherever, whoa, didn't know I could do that. 10. Right now I'm above the potassium chloride line. So this is what represents solubility. That's the maximum. I've got more than the maximum. So if this hasn't crystallized, it'll want to. But if it hasn't crystallized, then it'll be supersaturated. All right, so then this next one, I have a saturated solution of potassium nitrate in 100 grams of water at 50 degrees Celsius. Let me pick a different color. So we've got a saturated solution in 100 grams at 50 degrees Celsius. So I can find 50 degrees Celsius, but how do I know how much is in the solution? Above the line is supersaturated, under the line is undersaturated or unsaturated, on the line is saturated. So on the line would be the maximum amount. And so here, since it says I've got a saturated solution, I'll go up until I hit that line, more or less. So that's something like, that's not straight. There you go. I don't know, 86. So we've got 86, degrees, 86 grams per 100 grams water. And now I cool it down to 20 degrees Celsius. How many grams of potassium nitrate crystallizes? So 20. Again, if I go up, the place that I'm going to go up to is the line, because that represents the most that I can hold. And Right? It says it crystallizes. So we're not going to assume that this is going to become a supersaturated solution. We're assuming that whatever extra is in the solution is going to form crystals, is going to precipitate and come out of the solution. And so here at 30, we can hold like, or at 20 degrees, we can hold about 30. So that's 30 grams. So if I subtract those, then I get something like 56 grams of KNO3 crystallizes. So most of the time, these recrystallization problems end up just being like, find out how much I have when it's hot, find out how much I could have when it's cold, and subtract the two. So like we could do the same for the potassium chloride, right? Because it becomes supersaturated, we figure out, well, what's this difference? If I started at 40 and I come down to, actually that one is also 30, so we get about 10. There's a trickier version of this problem because all of these were in 100 grams of water. But what happens if I instead have 200 grams of water? Just double it. If you have half the water, then it'll be half. What gets a little bit tricky is then going and reading these, like here, just work off of, I've got 100, and then sort of convert it at the end. I don't think I'm going to bother with, since we're not doing an example, I won't bother with putting one of those on the final. All right, so solubility is kind of a version of solution concentration. So solution concentration is the amount of solute, which is green, because I arbitrarily picked colors earlier, in an amount of solution. And there's a bunch of different ways that we could define this, because there's a bunch of different ways that we could define amount. Amount could be moles, amount could be grams, amount could be liters or milliliters or 100 grams of water. And so solubility is sort of one definition where, oh, actually I think, yeah. That's grams of solute divided by grams of solvent, usually 100 grams of solvent. But another one that's a little bit more useful actually is mass percent. Now in mass percent, we make a change. And instead of saying mass of solute, in just the mass of the solvent, we add up those masses together. So mass of solute divided by whatever the mass of the solute plus the mass of the solvent is. And really this is more convenient because it's calculating the mass of the whole package. Because if I take 100 grams of water, just look at this. If I take 100 grams of water and I add 36 grams of NaCl to it, how much is the whole solution going to weigh?
Feels like a trick question.
It's not a trick question. It's not a trick question. 136, right? The mass of the water is, or the mass of the salt is still in there. So if I mix those two things together, it's the whole mass. This is why the answer to the question, if I eat a 1 pound burrito, am I 1 pound heavier? The answer is yes. Yes. I added 1 pound of mass to my body. Now, is my like actual body weight, like after 8 hours, will I still be 1 pound heavier? No. But actually the weirder question is, what happens to that 1 pound? Yeah. Pretty much everything you eat gets exhaled as carbon dioxide. Anyways, we won't go more into that. So if I add these together, that's it's 136 grams. That's a significant amount more massive or heavier than 100 grams. So a lot of these solutions, they've got solute, and we want to add that to the solvent. Did I? So really what we want is the mass of the solute divided by the mass of the solution. Solute, but now solution on the bottom. This is one of the places on these, like on an exam question that you might get tripped up, is that if it's asking for mass percent, I might give you the solvent mass and I might give you the solute mass, solute, and then ask you to calculate mass percent. You have to add these two together to calculate the mass percent, because I need the mass of the solution, not just the solvent. So let's do some examples. All right, so we want to calculate the mass percent of a sucrose solution containing 100 or 11.3 grams of sucrose, 412.1 milliliters of water, and then we're going to assume the density of water is 1 gram per milliliter. If you remember this trick from a few labs ago, I can take my 400 and, well, actually here, let's not put the cart before the horse. So what I want to find is mass percent, which means that I need the mass of the solute, and I need the mass of the solution. So question for you, in this problem, what is my solute?
The 11 grams of.
Yeah, it's the thing that I'm dissolving. Usually it's solid. Sucrose is a solid. Water, just say it, is almost always going to be the solvent. Which does bring me to the next question. How do I get the mass of the solution? Oops. Close, close. It's going to be the mass of, right, so solution, which is a mass, solution is going to equal the mass of the solute plus the mass of the solvent. So we already know what the solute is, that's the sucrose, but what's the solvent? Oh, I used the wrong colors. Yeah. This doesn't matter yet, but I used these colors later, so solute always has to be green, solvent always has to be blue. So my solvent in this case is going to be water. Like I said, almost always going to be water. The problem then is, okay, I have the mass of the solute, right? It's just 11.3 grams. If I want the mass of the solvent, mass means grams, whether it's kilograms, micrograms, milligrams. But I have milliliters. That's okay though, because if I take 412.1 milliliters and I use the density, 1.00 grams per 1 milliliter, then that is also 412.1 grams. So then my mass of the solute is 11.3 plus 412.1, which gives me anybody calculate that yet? For 23.4 grams. Solution. So then I can take my, really kind of made a mess of things here. 11.3 grams of the solute divided by the whole thing, and then we'll multiply that by 100 to give me a percentage. So that is 2.67% sucrose by mass. Two, 6, 7. Okay, so that's how you would calculate a mass percent. It is kind of important to say that it's like percent by mass. I mean, if the question is asking for that, it's not that important. But in any other situation, there's other ways that you can calculate percentages. Actually, for the lab this week, you have to calculate weight volume percent, which is grams per milliliter, which is weird, but that would give you a different number than this. Now, when you use percent mass in a calculation, this is the same. This is actually exactly the same as the percent mass that we used way back in like chapter 6, I want to say, where it was like the grams of one element per grams of a whole compound. Same kind of thing, in that we want to take this 11.5% sucrose and we want to convert that immediately into 11.5 grams of sucrose per 100 grams of solution. That gives me a nice conversion factor, whereas percentages, not so nice. So how much sucrose in grams, which tells me what I'm looking for, how much sucrose in grams is contained in 355 milliliters of a soft drink containing 11.5% sucrose. Assume a density of 1.04 grams per milliliter. So very similar to the previous problem. And on this one, you could use, the advice that I always give is start with the number that's not a conversion factor. Or another way to put it is to start with the loneliest number. So just at 11.5% mass, conversion factor. You might be solving for that conversion factor sometimes, but it's a conversion factor. Density, conversion factor. Unless the problem's asking you to solve for density, that's a conversion factor. 355 milliliters, that's only got one unit. So that's the loneliest number. And now I can kind of take my other conversion factors and just kind of line them up and see where they take me. So 355 milliliters times 1.04 grams per milliliter times 11.5 grams of sucrose divided by 100 grams solution. So 355 times 1.04 times 11.5 divided by 100 equals 42.5 grams of sucrose. So percent mass, just a conversion factor. For some reason when I say that, I feel like I'm saying age is just a number. 33 is coming fast. All right. So I know it's not even that old. Right. Okay. So percent mass is great. There's a lot of places where percent mass is great. It can make for very easy calculations. It gets used a lot in soil science. If you're trying to calculate the percentage of like potassium in a soil amendment, some massive amendment gives you that a mass of potassium or sodium or phosphate, whatever you're looking for. Now in chemistry, we use moles. So we want a unit of concentration that gives us moles. And most of the time, because we're working with solutions of water, in fact, we want it also in terms of liters and not in terms of mass. Now these end up being a little bit interchangeable because you can use density like we've seen in the previous two problems. But molarity is going to be the unit that we use the most, because it gives us moles of solute again. Sorry, that should be green. Moles of solute per 1 liter of, again, solution, not solvent. Usually the solvent here is water, but liters of solution. There's actually, should go try and find that TikTok again. If you take, there are some things that you mix together, like 2 different liquids even. So if I take 100 milliliters of water and I add like 40 milliliters of ethanol to it, the volume ends up being less. Like the volume is less than 140. Because the ethanol and the water mix together really well, and it ends up in a sort of more compact structure of the water, which is weird. Most of the time, we're going to ignore that. We're mostly adding solids to a liquid. So this is per liter of solution, not per liter of solvent, so it's the whole thing all together. Again, which most of the time means that the volume is not going to change, so volume in liters. And the units of molarity are moles per liter. They're moles per liter. The units of molarity are moles per liter. The units of molarity are moles per liter. The units of molarity are moles per liter. The units of molarity is moles per liter. You should make this your mantra. Cannot tell you the number of times that this saved me when I was taking general chemistry just to remember this, because it makes it a conversion factor. So actually in lab today, we used sodium hydroxide, and that was 0. So actually in lab today, we used, I think technically 0,0, but it didn't say that on there, molar NaOH. This does not look like a conversion factor. But the units of molarity are moles per liter. Someday I'll write a catchy song. Catchy and annoying song. So to rewrite this, 0,0,100 moles of NaOH per 1 liter. Now that's a conversion factor. If I have liters of that solution, I can calculate moles. If I want to know how many moles or how many liters would contain a number of moles, then I can flip that. I mean, actually, to really emphasize this, there's a lot of ways that this can be written. So molarity is moles per liter, or moles slash liters, or moles over liters, or like 1.1 molar sodium hydroxide, which is 1.10 moles over 1 liter, or 1.01 or 1.10 molar sodium hydroxide means 1.010 moles of sodium hydroxide in 1 liter of solution, or 1.10 molar sodium hydroxide equals 1.10 moles slash liters of sodium hydroxide solution. I just kind of wanted to show you a bunch of those. It's a conversion factor. We usually use it as a conversion factor, although sometimes you will be asked to calculate it. So like in this example, how many grams of sucrose are contained in 1.5, or actually no, we're calculating grams, sorry. 1.95 liters of 0.781 molar sucrose solution. And what is molarity? Moles per liter. 0.781 moles of sucrose over 1 liter. And I will tell you this, right? I would not be talking like a crazy person about this if I didn't see this mistake made every semester. Please. I would be so happy. I would be so happy if on the final, everybody, for every single time molarity was on the page, everyone rewrote it as moles per liter. That would make my year. And there's not much left. If literally everybody who takes the final. Okay, so we want to find grams of sucrose. We now have a conversion factor from liters and moles of sucrose for this solution. The loneliest unit. Okay, so 1.95 liters is the loneliest unit here. It's not a conversion factor. So if you have no idea where else to start, write that down first. But now, since I wrote out 0.781 moles, and by the way, the number part of this always goes with the moles. Always. Every time, always. That's why this one, right, the 1.10 goes with the moles, goes with the moles.
Oh, so you mean the molarity cells?
Yeah.
Okay.
So if it's 3 molar, that's how many moles per liter.
This like okay, that makes sense.
Oh, yeah. Okay, so now I have this conversion factor, which is molarity, which is moles per liter. And that's sucrose. That's what I want. And then I also have conversion factor, because this is kind of a bear to calculate. I put it in there. The molar mass, which is grams per mole. Which again, like molarity, how the number part goes with moles, the number part goes with grams. So 1.95 times 0.781 times 342.34, 521 point, yeah, grams of sucrose. Now, this is the easiest version of this problem. You got to start somewhere. I mean, it could ask for just the moles. Could go the other way too, right? How many liters of this solution contains 521 grams of sucrose? I think that might actually be the next question pretty much. Oh no, this is just calculating molarity. Maybe this is easier. So the tricky thing about this one, so calculate the molarity. Molarity is moles per liter. Molarity, which means that we're actually finding moles per liter, is made by putting 55.8 grams of sodium nitrate into a beaker and diluting to 2.5 liters. It doesn't say water here, we're just going to assume. So what I'm looking for is moles of NaNO3 per, and actually we want to find it per 1 liter. The trick here is that we're going to start with however many grams, convert that into moles, and then divide that by 2.5. Because I've got 2.5 liters. If I divide by that 2.5, then the denominator becomes 1. But I need to find this part. Moles of NaNO3. So this is a way that this problem, or my typical advice of use the loneliest number. I've got 2 lonely numbers here. The 55.8 grams, that's 1 unit. So that's a lonely number, but the 2.50 is also a lonely number. Now, because I've already written it out, the 2.5 liters is already going to be used here to find the moles of sodium nitrate. The grams makes the most sense. So 55.8 grams of NaNO3 times, we need the molar mass. Sodium is 22.99. 84? What was it? 84,994? Perfect, thank you. And then 1 mole. And then I assume you already calculated this. I still appreciate you. And on this, I'm going to go all the way out to there just because. So that's how many moles of NaNO3 gets added to this amount of water. And so I'm taking that moles, I put it in this amount of water, and it spreads out into all that amount of water. Now to keep things, I guess this technical term, normalized, we're not going to talk about it in terms of 2.5 liters because that's really specific to this one case. But in general, the molarity would be how many moles in 1 liter. So I guess, is my final answer going to be more or less than this number of moles? Less, right? Because it's not in 1 liter, it's in 2.5. We're spreading it out. So that whole long number, only long because I made it long, goes into there, and we divide by 2.5, and we get 0.263 moles of sodium nitrate per 1 liter, or we could write this out as 0.263 molar and 3. And this is something that you guys never have to do. In hindsight, this is kind of wild, but when I was an undergrad, I had taken Chem 1, Chem 2. Then I was allowed to be the lab tech for Chem 1 and Chem 2. And I just had a key to the lab stockroom, and the professors would tell me what they needed for their labs, and I would go and make it. They had to show me, like at first, but then I was just allowed to work with the concentrated nitric acid and the concentrated sulfuric acid. And so like all the solutions that we use in lab, they get made from stock solutions.
I mean, granted, they are chemicals that probably shouldn't work.
I don't know. It's just like we don't do that here. Like if there's a student, like they have to have, I don't know. This is a small college. Yeah, completely unsupervised. Like I was just allowed to go in whenever. So to make this, you'd use like a special flask, a volumetric flask. These are very good for making a specific volume. Like this would be like probably, oh yeah, a 1 liter. It only measures 1 liter, kind of like the volumetric pipettes will do 5 milliliters or whatever. Larger volumes though. So you add in whatever you're going to dissolve, you add some water, you mix it, because it turns out when this is filled all the way up to there, it's very hard to mix. Like if you ever take a water bottle and you like put a cap on it, like fill it all the way up to the top, no air at all, put a cap on it, try to mix that.
It's like stuck on the top.
Yeah, it either like mixes it just the top. So like whenever I get like a protein shake, I always shake it this way because then the bubble moves around and mixes it. If you don't do that with one of these and you're working with a very, very particular scientist and they need really, really like specific concentrations that are completely mixed, and you do the dumbass thing and you fill it up to here before mixing it, then you got to stand there and you go flip it up so the bubble goes up, and you go back and the bubble goes up, and then you turn it and then it goes up and then up and then turn it and up and up, and you have to do that 50 times. No, definitely not. I would never. It was probably more than, I think it was maybe more like 100.